Okay, this is another one of our trig review videos. VIEW trig review video. And for this particular one, I'm looking at a handout I've got over here on the other side. This is titled Nuggets of Trigonometry for the Exam. What I've done here is I've taken the entire course and I've distilled it down to one page. So that if you can know all of the information on this page and their applications, then you should know everything you need to know for the exam. Okay, for this video, I'm going to come down and look at a little bit of the angle measurement. Over here again, angle measurement and arc length and sector area formulas. These sort of go together. So this should be a short video, I think. It's based on two formulas, arc length of a circle, so picture a circle with a given center and radius, and an angle, a central angle with a given measurement here. Okay, so you have the angle theta, and your task is to find S. S is the letter we use for the arc length. It's what's the length of that arc right there. And the arc length formula is rather simple. S is simply going to be R theta. And an example of that coming up. The second topic in the same section was the sector area of a circle, and area is traditionally used A. So once again, we have our circle, and once again, we have a given radius and angle, and now we're asked to find the area of this piece of the circle, the interior of the circle. Okay, so what's the area there? And again, the formula is rather straightforward. Area is 1/2 r squared theta. Now, both of these require that the angle, this central angle that's illustrated in both ones, theta, must be in radians, not degrees. The formulas are actually much more complicated in degrees, and you can come up with equivalent formulas if you like. But let's go ahead and pull up another page. We'll come back and give a couple of examples of this in just a second. But the question is, what is a radian? What is a radian? It's a way of measuring angles that relates arc length to radius. So obviously it's tied into this idea of arc length is r theta. And here's the basic idea. Let's say you have a circle. And again, the circle is one of the basic conic sections. X squared plus y squared is r squared. If you're centered at the origin, it really doesn't matter for this presentation where the center is. But we have a circle, and we have a known radius r. If you take that radius, pretend you took that radius, and you put one end of it on the circle, anywhere on the circle, and then you took the other end, this end here, and you started to wrap it so that, if this were a piece of string, what I would be doing is having this end fixed, and then I'd run the string so it goes to about there. This length, this R length, is now pinned to the circle and wrapped up to about there. So this is R going this way. Okay? So if you do that, and then you go back and look at the circle with the angle here, by definition, the measure of this angle is exactly 1 radian. 1 radian. It works out to be, you know, around 60 degrees. Obviously, this is not a 60, 60, 60 triangle because one side is curved, and this is a curved side, and these two are straight. But it's about 60 degrees, and we'll come up with a formula and actually get it exact in just a second. Okay, so let's suppose you had, let me pull up another circle again. Suppose you wrapped the radius twice. So once again, here's your radius, and you pull that off to the side, and you think, okay, I've got this length. This is the R, and I'm going to pin there, and I'll go, there's 1 R from here to here. But suppose I duplicated it. There's 2 R's from here to here. 2 R's going all the way from there to there. And suppose I go 3 R's. No, well, all the way over here. This is 3 R's. Okay, to that point. And then here's sort of the magic number. If I went all the way to here, like a complete half of a circle, 180 degrees, okay, how many R's would that be? How many radius units would that be? Well, let's see what we know from geometry. We know the circumference of a circle is 2 pi r, 2 pi r. So the circumference is not really a circumference, but half of the circumference, like let's say the circumference of a semicircle, would be 1 pi r, 1 pi r. So let's suppose we've done this now. We've got 1 r here. We've got 2 r's to here. We've got 3 r's to here. What does pi r's look like? Well, pi r's is about, first of all, 3.141 radiuses. And sure enough, that would be this length of the semicircle. That would go all the way to here. So this entire top half of the circle has a length of pi. And in fact, whether you know this derivation or not is, I'm not sure that's terribly important. But what you do need to take away from this is the idea that 180 degrees is exactly the same as pi radians. These two represent the same quantity. So a half of a circle, 180 degrees. You can think in degrees, no problem there, 180. But what we want to do is we want to be able to think in radians. So this is exactly pi radians. And there's no unit symbol with radians, so we just write the number pi. Of course, that leads to all the other, you know, bits and pieces. 90 degrees. 90 degrees would be a half of pi, so that would be pi over 2 radians, and so forth. So all the breakdowns in your unit circle. Now, let's go back to our 2 formulas on this previous page. Our task is to find the arc length in a problem, right, or the sector area in a problem, given the radius and the central angle. Okay, so given the radius and the central angle, find the arc length. But again, the angle must be in radians. Okay, so let's do a couple of simple problems. We have a circle. This is equal to 3 centimeters. We have an angle here that's exactly 1.3. And the question is, how long is the arc length? How long is that arc length? Okay, so it's an arc length problem. Here's your formula. S is equal to r theta. So the arc length is going to be the radius, which is 3 centimeters, times the angle, which is 1.3. So we get 3.9 centimeters. Now, the first time you see a problem like this, you go, well, what do you mean the angle is 1.3? That's a perfectly good way of measuring angles. You say, well, I never did that in geometry. I always used a protractor, and I had degrees. Okay, so let me give you an equivalent problem where the angle is given in degrees. We have our circle, and we have a radius. This time we're going to make it inches. So this is 5 inches. And I'm going to give you this, and that looked to be, I don't know, maybe about a 80-degree angle, say an 85-degree angle. And the question is, what is the arc length? Okay, so we have to go from here to here, and the question is how long is that part of the circle? So once again, we grab our formula. S is equal to r theta. So the arc length is going to be 5 inches. But now the angle is not given in radians. So this problem is much more difficult. Let's see, we have 85 degrees. Somehow we have to convert that to radians. So the conversion factor is 180. Oops. It's going to be pi divided by 180 degrees. Okay. Because we said on the other screen that pi is the same thing as 180 degrees, anything divided by itself is the same as 1. So pi divided by pi is obviously 1, and 180 degrees divided by pi is going to be 1. Likewise, if we had pi is 180 degrees, we divide both sides by 180 degrees, that's going to be 1. Pi divided by 180 degrees, that's going to be 1. So I'm using this particular fact right here. I'm multiplying my 85 degrees times 1, and I get, let's see, the degree units cancel, which is nice. So now I just get 85 pi divided by 180. Okay, and that will reduce. Let's see, obviously 5 goes into both. So what's that? 117 pi, and 5 goes into this 36 times, and that's about as simple as it gets. Okay, so I now have my angle in radians. I can go back to my formula and just plug in 17 pi over 36. Okay, and that would be the arc length in this particular problem. This arc length, this portion of the circle, is going to be 5 times 17. What's that? 85. So we have 85 pi divided by 36. This is an arc length now. Make sure you have the units. And in this problem, it is inches. Okay, so we'll sort of clean that up there and go, this is what S is equal to, okay, arc length. Okay, and again, just looking back at the previous problem, way easier if the angle is given in radians. So 1.3 was a much, much simpler problem. All you had to do was multiply r times theta, and you're done. Okay, oftentimes in the unit circle, the angle is given at increments of pi. In this problem, we gave the angle in degrees. That's not a nice breakup of pi. It just happened to be 85 degrees. One more arc length problem where the angle is given as a section of pi. So let's see, let's suppose this is our radius again. Let's do meters this time. So this is 17 meters. And we have the angle here, and this is going to be 2 pi over 5. This is the center of the circle here. And the task is find the arc length from here to here. What is S? Okay, so we have the radius and we have the angle. Angle's given in radians, so this goes very quickly. S is r theta. S is going to be 17 times 2 pi over 5. And so what do we got? 34 pi over 5. Carry the units along with it. Remember, this was 17 meters. So there's a meters here, and there's a meters here. Done. Okay, so the arc length, 34 pi divided by 5 meters. If you wanted a decimal approximation, certainly you can grab your calculator on that and get an approximately so many meters. Okay. That's it for arc length. Let's do sector area, a couple of problems. And again, the idea is you have a circle, you have a radius given. Let's say this is 3, I don't know, feet. Okay, and you have an angle given. Let's make this 3 pi over 4. And the task is to find the area of the sector. And this is called a sector. It's a portion of the interior of the circle. Okay, so here's your formula. The area is 1/2 r squared theta. And again, theta is in radians. So we have everything given to us in this problem, so we can just write down our answer. The area is going to be 1/2 3 feet squared. Notice, by the way, squaring the feet is going to give us square feet at the end, which makes sense. This is an area problem. Times theta, which is 3 pi over 4. And we should just go ahead and clean that up. Things go reasonably well here. Let's see, on top, we have 3 squared is 9 times another 3 is 27 pi. And on the bottom, we have 8. So 27 pi eighths square feet. And again, you can go to a calculator and get an approximation there as to how many square feet that is. Okay. Now, of course, both of these types of problems, arc length and sector area, can be worked backwards, where I may give you one and ask for, I may give you the arc length and ask for the radius, or I may give you the area and ask for the radius, or I may give you the area and the radius and ask for the angle. I mean, there's lots of ways you can work these equations. Remember, S is r theta. If you know any two, you can calculate the third. So we've done it that way. Suppose I told you S is 10 inches, and I told you that the radius was 3 inches, and the task is find the angle, theta, to the nearest thousandth of a degree. And this is what we're going to do in degrees. Thousandth of a degree. Okay, so there's going to have to be a conversion sooner or later. Let's go ahead and, if you want to sketch, you can. That's not a bad idea. We have a circle. The radius is given to be 3 inches, and the arc length is given to be 10 inches. Now, 10 is 3 1/3 inches. Well, if we go from here all the way to there, that's going to be pi inches, which is about 3.14159. Okay, but we're going 10 inches, which, let's see, which is going to be, well, I said 3 1/3. That's silly. It's going to be 3 1/3 radiuses. Okay, so here's one radius, here's 2 radiuses, here's 3 radiuses, and another little bit is going to go to there. So I'm not sure that you need the picture here. The formula works very well without a sketch. But this is our arc length from there to there. That's 10 inches. And that's going to be a little bit more than pi. Okay, so I said pi is 3.14. That would be for the angle. Let's see if we can clean this up a little bit. This angle here is pi, or 180 degrees. Remember, the arc length is r theta. So for 180 degrees, the arc length would be 3 pi, right? Radius is 3, right? And the arc length is pi if we're just doing a semicircle. And 3 pi is about 3 times 3.14-ish, which is about 9.42. Okay. So, but we're going 10 inches. So we are certainly going more than 180 degrees. This is our arc length. And the task now is to find the measure of theta. So here's our angle. This theta that we're looking for is more than 180 degrees. Probably wouldn't have seen this problem in geometry. Geometry, we normally restrict angles to less than 180. Okay, let's go ahead and plug in the stuff and solve for theta. Here's our formula. We were given arc length, we were given radius, we just need theta. So let's see, S was 10 inches and radius was 3 inches, and theta we don't know. So theta is going to be 10 inches divided by 3 inches, and the inches cancel. So theta is equal to 10/3. Okay, so there's our angle. It is in radians, right? But the problem said write this to the nearest thousandth of a degree. So we need to convert this 10/3 to degrees, and we need a conversion factor again. We want degrees, so I'll put 180 degrees here and pi on the bottom, okay, because again, the idea is 180 degrees is exactly the same as pi. So if I divide both sides by pi, that will be 1. And so I'm multiplying 10/3 times 1, and when I get 3 goes, I'm going to grab a different color here, 3 goes into 180 60 times, so that gives us 600 degrees on top and pi on the bottom. Okay, so 600 degrees divided by pi. And now I suppose we should go ahead and go to our calculator to get an approximation to the nearest thousandth. Let me stop this while I pull up my calculator. Okay, back again. I've got my calculator here. So now I just need to multiply or divide 600 degrees by pi. 600 divided by pi gives me about 190 degrees, 190.98. We need the nearest thousandth. Let me 986, rounding 986 degrees. Okay, so there's a problem on sector, or on arc length. And one last problem, we'll make this quick, on sector area. Suppose I have a piece of pizza, and I tell you this happens to be 30 square inches of pizza, and I do tell you that this happens to be 135 degrees. 135 degrees, and the question is, what was the radius when we started? Okay, so it's a circle. It's supposed to be the center of the circle there. We have a pizza, and this particular slice of the pizza, 135 degrees with the angle, has 30 square inches of pizza stuff in it, and the task is how big a pizza, what was the radius of the pizza. Okay, so here's your formula. Area is 1/2 r squared theta. We have the area, which is 30. We don't know r, so we're going to leave that alone. We do know theta, though, which is 135 degrees. Unfortunately, we need it in radians, so we'll multiply by pi over 180 degrees. Again, this expression here is exactly equal to 1. And so we'll clean this up a little bit. We have 30 is 1/2 r squared. Let's see, if we simplify this fraction right here, and your calculator will be available for most of the exams. So 135 divided by 180, sure enough, exactly 3/4. So this is 3 and this is 4. So let's see, we have 3 pi over 4. So again, a little bit more arithmetic here. We've got 3 pi r squared over 8. I'm trying to figure out what r is. Multiply both sides by 8. 240 is 3 pi r squared. Divide both sides by 3 pi. So I have r squared is 240 over 3 pi, or r squared is 80 over pi, right? And so now I'll go to my calculator. 80 divided by pi is that number, and we want the square root of that. So r is going to be the square root of 80 over pi, which to the nearest thousandth anyway is going to be, let's see, square root over here. Square root of that answer is about 5.046 inches. So it sounds like this was a little tiny personal pan pizza with a radius of about 5 inches. Okay, so let me go ahead and stop the video here, and this will be just recorded as arc length, sector area, and radians.